Hello friends, organic reactions and thermodynamics. That is our topic for discussion today. So thermodynamics, we won't go too much in detail, but only the essential concepts which is relevant to our subject, that is organic chemistry, that is thermodynamics in connection with organic reactions and organic reaction mechanisms. Now, all of you know endothermic reaction and exothermic reactions. You are familiar with this in any chemical reaction if you take it. If energy is absorbed, energy, heat, it is absorbed. The reaction is known as endothermic reaction. And when energy is released or when energy is liberated, the reaction is exothermic. One is energy is absorbed, endothermic, energy is released, exothermic. Okay, but these are all very simple kind of a definition here. So we will go slightly in more, in detail about endothermic, exothermic reactions here. Okay, now we will examine. Now we have seen this homolytic cleavage. Okay, that is a bond AB, for example. Is a molecule bond AB. It is, the breaking of this bond homolytically. That is A plus B. That is, the electrons are equally divided here. Homolytic cleavage, you know that. AB bond is broken and two radicals are formed here. Now, you see the bond, how the bond will break? Only when the energy is applied. The energy needed to homolytically cleave a covalent bond. This is AB, it's a covalent bond. For breaking this covalent bond into radicals here, that is homolytic cleavage. Okay, so we need energy. Energy is to be supplied to the molecule here. Okay, the energy needed to homolytically cleave is a homolytic cleavage of the covalent bond. Okay, this is known as bond dissociation energy. Bond dissociation energy. So a bond dissociation energy, it is for a specific kind of reactions. So here we are talking about a homolytic cleavage of a covalent bond here. So bond dissociation energy, it is usually represented by this symbol delta H. We are putting a superscript here, degree. This it indicates that the bond dissociation energy, it is delta H here. So this means the values here, they are determined under standard conditions. So standard temperature of 25 degrees Celsius and an atmospheric pressure and all this kind of a thing here. Okay, so this is bond dissociation energy here. Correct. Now delta H here, it is the energy absorbed or released. Now here in this particular case, it is a bond dissociation energy, a bond, covalent bond AB. When this energy is applied, the bond will break into the free radicals here. Okay. Now delta H generally, it is the energy, it represents the energy absorbed or it is the energy released in any reaction. Okay. Now this is known as delta H. It is a enthalpy change. Okay, briefly I will discuss all these concepts here: enthalpy, entropy, free energy, and all this kind of a thing here in thermodynamics. Okay, so delta H, it is the energy absorbed or energy released in any reaction. So it is called the enthalpy change. Enthalpy change, we can also call it heat of reaction. Enthalpy or heat of reaction. All changes only, enthalpy change we are talking about it. Okay, heat of reaction here. So now when delta H is positive, if it is positive, and delta H can be negative, value of delta H can be positive and value of delta H, it can be negative here. Okay, when delta H is positive, energy is absorbed. Okay, and the reaction is endothermic reaction. This is endothermic reaction. Correct. Now when delta H is negative, energy is released. This is known as exothermic reaction. Two types of reactions here. Okay, in simple terms, delta H is the bond dissociation energy. That is the bond, AB bond. It is actually dissociating, it is breaking. That energy is needed for that. So delta H is positive means endothermic reaction. That means energy is to be supplied, and delta H negative is exothermic, energy or heat is released here. This is the enthalpy change or heat of reaction here. Now bond breaking, it requires energy, you know that. Therefore bond dissociation energies are always positive. Okay, bond breaking or the cleavage of a bond, it requires energy. Therefore this bond breaking, it requires energy. Therefore bond dissociation energies, it is always positive. No, positive numbers. Correct. Bond dissociation energies are always positive numbers here. Therefore homolysis, if you take it, this is the homolytic reaction here. Homolytic cleavage, you know that, homolysis. Okay, therefore homolysis, it is always endothermic, because for breaking the bond we have to supply energy, that is delta H is positive. Therefore homolysis always is a endothermic reaction here. Conversely, if you take it, now the bond formation always releases energy. Correct. Therefore the bond formation, that reaction is exothermic. Bond breaking, endothermic. Bond formation, forming, it is exothermic. Okay, so bond breaking, it requires energy. Therefore bond dissociation energies are always positive numbers. Correct. Therefore homolysis, it is always endothermic reaction. Okay, the other way around, if you see the bond formation, okay, bond formation always releases energy here. So the reaction is exothermic. Bond breaking, bond formation. Okay, bond breaking is endothermic and bond formation is exothermic. Correct. Now the bond dissociation energies, we can compare it with the bond strength. Correct. Bond breaking is endothermic and bond breaking is exothermic, you know that. Now bond dissociation energy, now we can compare it with the bond strength. Dissociation energy comparable with the bond strength. That is, the stronger the bond, the more the energy needed to break it. Okay, that is the bond dissociation energy, we can compare it with the bond strength of the bond here. Okay, it is equivalent to comparing bond strength here. That is, the stronger the bond, we can say, stronger the bond, the energy needed, it will be very high here. The higher is the bond dissociation energy. Now shorter bonds, we know, shorter bonds are always stronger bonds. Okay, shorter bonds are stronger bonds. Now stronger the bond, the higher the bond dissociation energy. That means the higher the energy needed for breaking that bond. Simple thing. Okay, now delta H here, it indicates the relative strength of the bonds also, indirectly we can say. Correct. The delta H, it indicates the relative bond strength here. Relative strength of bonds broken. Bond strength means strength of the bonds broken as well as strength of the bonds formed in the reaction here. Okay. Now overall delta H, if you see delta H positive means what? Let us analyze it fully. Now delta H positive in a reaction, overall reaction, if you see, delta H positive means more energy is needed here. More energy is needed to break the bonds here than the energy released. Okay, more energy is needed for breaking the bonds than the energy released during the formation of the bonds here. That is, the bonds broken, okay, in the static materials, they are stronger bonds, because we know that the stronger the bond, the higher the energy needed to break that bond, higher the bond dissociation energy. Therefore in a reaction, if you see, if delta H is positive, that we have to interpret in this fashion, that more energy is needed, okay, to break the bond compared to the energy released during the formation of the bond here. Therefore the stronger the bond, which is the bond here, which is stronger bond, the bond in the static material, the bonds broken in the static materials are stronger, okay, compared to the bonds formed in the product stage. Okay, static material stage, product stage. The product stage, the bonds are formed. Those bonds are weaker compared to the bonds broken in the static material. Okay, now that is delta H positive here. Now delta H is negative means what? Okay, delta H negative means more energy is released. Delta H positive means more energy is applied for breaking the bond. Now delta H negative means that is more energy is released, okay, in forming the bonds than is needed to break the bonds here. Correct? That is delta H negative. The energy released is more compared to the energy needed for breaking the bonds in the static material here. Okay. Therefore, the bonds in the products are stronger than the bonds in the static materials. When delta H is positive, it is the other way around. That is, the bonds broken in the static materials are stronger than the bonds formed in the product stage. Okay, when the delta H is negative, more energy is released in forming the bonds. Correct? Forming the bonds than the energy needed for breaking the bonds. Correct? Therefore, the bonds formed in the product, they are stronger than the bonds broken in the reaction material. That is static materials here. Now, so let us see in a reaction in which, I'll change this page. Now, in a reaction in which, say, several bonds are broken and several bonds are formed, what will happen? Okay, several bonds are broken, several bonds are formed. Then what will be the total enthalpy change? That is overall enthalpy change. That is what we are concerned here. Overall enthalpy change in a reaction. That is what we are just discussing now. And this is a positive value and negative value here. How will this is the thing. That is overall enthalpy change. That is the total change of enthalpy. It will be sum of, that is many bonds are broken, many bonds are formed here. Therefore, delta H here, that is overall enthalpy change. It will be delta H of the bonds broken, sum of, we can say, delta H of bonds broken plus sum of, this is a negative sign because energy is released here, sum of delta H of bonds formed. Correct. Simple equation. So it is always a positive value here. Delta H of bonds broken is always positive because energy is needed. This is always a positive value because energy is needed. Delta H of bonds broken means that is energy is needed to break the bonds. Correct. Therefore, sum of the dissociation energies of all bonds broken in the static material. Correct. So here sum of delta H of bonds broken means we can say it is because it is a positive digit, positive number, because the energy needed, okay, to break the bonds, total energy needed to break the bonds in the static material. Therefore, it will be sum of the dissociation energies of all bonds broken in the static material. Okay, here that is the delta H bonds formed. It is sum of the bonds, okay, bond dissociation energies of, okay, we are concerned with the bond dissociation energies here. Bond dissociation energies of all bonds formed in the product stage. Okay, negative value shows energy released in forming the bonds here. Okay, negative means energy is released in forming the bonds here. Okay, here in the case of bonds broken means that is the energy needed to break all the bonds. That is the sum of the bond dissociation energies of all the bonds in the, all the bonds broken in the static material. That is in the reactance side here. Okay, and now the second part here, sum of the delta H of bonds formed means the sum of bond dissociation energies of all the bonds formed, okay, in the product stage here. The negative value, it will show energy released in forming the bonds here. So this is how we have to calculate. Okay, the bonds broken, that is, it is related to the bond strength here. Bond dissociation energy, it is related to bond strength. Okay, now let us see in a reaction of this type. If you see, I can just show you an example here. the delta H, overall enthalpy change. How will you determine the overall enthalpy change here in this reaction? That is, we have CH3, say thrice Cl. Okay, a compound. Then it is reacting with water. Okay, HOH. Then we are getting a compound CH3 thrice COH plus HCl. Okay, we are getting a reaction of this nature. Now the bonds broken. Which are the bonds broken here and which are the bonds formed here? This is the only thing which we will have to see here. The bonds broken are CCl bond here. Okay, CCl, this bond is broken. Then this bond is broken here. Two bonds are broken here. Now what will be the dissociation energies here? Delta H. Okay, here delta H, we can get it in kilojoules per mole. Okay, here we can get it from the tables, kilojoules per mole. So this is actually found to be 331 kilojoules per mole, and this is seen to be 498. Correct? Therefore, the total energy needed to break the bonds, it will be to the tune of, say, plus 829 kilojoules per mole here. Okay, this is the energy needed for breaking the bonds. This is for bond breaking. Now, bonds formed. Which are the bonds formed? Bond forming. Let us see the energy here, dissociation energy. The bonds formed here, it will be, these are the bonds formed here. CH3 thrice COH. This is the bond formed here, one bond. So here the energy is seen to be minus 401, that is kilojoules per mole. This is the delta H. Okay, forming this new bond here. The another bond formed will be HCl. Okay, so here it is seen to be 431. So total it will be minus 832. Okay, kilojoules per mole. This is the delta H here, that is energy released in forming the bonds. The first thing is energy required for breaking the bonds here, and the second one is the energy released in forming these bonds here. Here if you see the difference here, sum of this thing will be plus 29 minus 832. So this will be minus 3. So minus 3 kilojoules per mole. So it is a negative value. Therefore, it is a negative. That is an exothermic reaction. That is, reaction is exothermic because energy is released here. Okay, the bonds broken in the static materials are weaker bonds. That is why energy is released here. Okay, here delta H is negative. That is delta H. It is a negative value. Negative value means the reaction is exothermic here. Okay, so how will you relate it with the bond strength here? That means the bonds broken in the static material, they are weaker. Correct? They are weaker compared to the bonds formed in the products. That is why the delta H is negative. That is, the reaction is exothermic and energy is released here. So this is the way you should compare the energy released in the reactions here. Okay, now thermodynamics, we will briefly, what is thermodynamics here? Concerned with energy and equilibrium. Okay, briefly we will tell you. So the thermodynamics means, why do you conduct reactions? Okay, we conduct reactions in the laboratory. So we conduct reactions in the industries, okay, for manufacturing the products. In the laboratory, we conduct experiments. And we'll be mixing up two reagents here, two chemicals, and finally you should get a product. Your aim is to get the product. That is the maximum yield of the product within the minimum time possible. Okay, there are two aspects here. First thing is the yield. That is, for a reaction to be a practical reaction, rather, a useful reaction, the equilibrium, because these are all equilibrium reactions. Dynamic, the system is dynamic. That means there is a continuous process of the reactants getting converted into the products and the products getting converted back to the reactants. So it's a dynamic system here. Therefore, a reaction to be useful or it to be practical, the equilibrium, it must favor the products. That is, we should get an optimum yield of the products here. Then only it will be profitable. Otherwise, it will be a waste of time for you. Okay, you don't have to conduct reaction there. Okay, so a reaction to be useful, that equilibrium formed. I will explain to you what is this equilibrium and all now. Equilibrium, okay, it must favor the formation of the products here. Okay, we have the reactants, that is starting material, they have the products here. So when this reaction proceeds, then equilibrium stage will be reached here. Okay, so these are the two conditions here. And another thing is the time factor here. Okay, the time in the reaction rate, it must be fast enough. Correct. So the reaction should be completed within a reasonable time. Most important thing. So that is another aspect of the reaction, that is a kinetics. Reaction means that is a theory, kinetic theory. I will be discussing it in the next class. Okay, so for the reaction to be useful or a practical reaction, we can say the equilibrium, it must favor the formation of the products here. Okay, and the reaction rate, it must be fast enough, rather than to complete the reaction within a reasonable span of time here. Okay, these two conditions, they depend upon the thermodynamic and kinetics of the reaction. That is thermodynamics of the reaction and kinetics of the reaction here. These two conditions, because these are most important things when you are conducting a chemical reaction. These are the most important thing here. Now thermodynamics means describes energy. In thermodynamics, we are concerned with the energy and the equilibrium. Correct. That is the relative energies of the reactants and the products. We are concerned with in thermodynamics the relative energies of the reactants and products here. Okay, and the relative concentrations of the reactants and the products. Okay, at equilibrium. So two things, that is in thermodynamics we are concerned with the relative energies of the reactants and the products and the relative concentrations of the reactants and products at equilibrium. Correct. So kinetics is concerned with the reaction rates. That means how fast the reaction is proceeding. Okay, that is how fast the reactants are getting converted into the products. That is kinetics. The rate of the reaction we are more concerned with in kinetics, whereas in thermodynamics we are concerned with energy. Energies of the reactants and energies of the products, relative energies and relative concentrations at equilibrium. Now, equilibrium means what? That is a reaction. It's a reaction condition, rather, equilibrium. This is the condition in the course of a reversible reaction. Okay, equilibrium and relative energies. You should have a fairly good idea about this thing. Reversible reactions. That is, the reaction will proceed in the forward direction as well as in the reverse direction, backward direction. That is, forward and reverse reactions are, they take place at the same time here. Okay, the forward reaction and reverse reactions take place at the same time. Okay, now the rate, at the same time, that is at the same rate. At the equilibrium, what happened? The same reactions take place at the same rate at equilibrium. That is, the forward reactions and the reverse reaction take place at the same rate at the equilibrium. That is a condition in the course of a chemical reaction, that no net change takes place in the concentration. Okay, at the equilibrium, what happens? The two opposing reactions, one reaction in the forward direction, one reaction in the opposite direction. So these two opposing reactions, they take place at the same rate. Therefore, the net concentrations of the products and net concentrations of the reactants, there is no change. Okay, it remains constant. It is not equal. Okay, the concentrations of the products need not necessarily be equal to the concentrations of the reactants here or the starting materials here. Okay, the concentrations, it doesn't change thereafter. A reversible chemical reaction is one. The product, as soon as they are formed, what happens? They react to produce the original starting materials, so the reactants here. Therefore, at equilibrium, what is happening? The two opposing reactions, the forward reaction and the backward reaction, go on at equal rates, and hence there is no net change in the amounts of substances involved. That is, the concentration doesn't change. At this point, we can say the reaction may be considered to be over, completed. Correct? It's a dynamic system. Forward and reverse directions. It is moving here. Now, the relative energies of the reactants. Now, we are concerned in thermodynamics, the relative energies of the reactants and relative energies of the products, they are determined by what? By the potential energy stored. Okay, potential energy stored within the molecule as bonds. That is, the bond has got a strength. For formation of the bond, when the bonds are formed, energy is released. When the bonds are broken, energy is supplied. Correct. Therefore, it is in the nature of a potential energy, we can say. Correct. So that is the relative energies of the reactants and the products. Yeah, okay. They are determined by the potential energy. Potential energy stored within the molecule. Okay, in the nature of chemical bonds, there are so many bonds. Many bonds are broken. I was telling you, many bonds are formed and many bonds are broken and all this kind of a thing. So these energies are stored in the molecules here. Okay, in the bonds, chemical bonds here. Okay, now for an exothermic reaction again. So let us examine the issue. Now the exothermic reaction, if you see, the products are lower in energy than the reactants. Okay, so resulting in a releasing of the heat. That is, when an exothermic reaction takes place, the products are lower in energy. Because of that thing, what happens? Energy is released here. Okay, products are lower in energy compared to the reactants. Therefore, energy is released here. But endothermic reaction is the other way around. The products are higher in energy, okay, than the reactants. Therefore, energy, requiring constant addition of energy. That is endothermic reaction. Endothermic reaction, the products are higher in energy. Therefore, we have to keep on supplying the energy there. Products are higher in energy compared to the reactants there. Okay, therefore requiring constant addition of energy. That we have to keep on supplying energy here. So all chemical reactions, we can say it involve energy. Correct? So either energy is used for breaking the bonds or energy released for forming at the time of formation of the bonds here. Chemical reactions means energy is involved here. Correct? Energy is used to break the bonds. We have seen break the bonds in the reactants. Okay. Then energy is released when new bonds are formed in the products here. So now let us examine an equilibrium, the concept of an equilibrium constant. What is meant by equilibrium constant? How it is all related with the energy and all. Briefly, equilibrium constant Keq. So simply we can say a starting material, say A plus B, in a reversible reaction, equilibrium reaction, it is giving the product C plus D here. A plus B, A and B are reactants, C and D are products here. Okay, so here Keq, that is the equilibrium constant, we know that it is actually the concentration of the products divided by concentration of the reactants here, or the starting materials, whatever you call it. Correct. So here equation will be the Keq, we can rewrite it as, that is C, concentration of C, concentration of D divided by concentration of A, concentration of B here. Okay, so this is the equilibrium constant. That is the concentrations of the product divided by concentration of the reactants here, starting materials here. Okay, now what is the significance? We say this is very simple. We can write it here. Okay, products divided by reactants. So the significance, there is a significance for this equilibrium constant here. It will tell you, so in an equilibrium constant is concerned with the equilibrium. So the equilibrium constant tells us about the position of the equilibrium. Correct? What is meant by position of the equilibrium? The position of the equilibrium means, that is the equilibrium constant, it will give you an idea whether the starting materials predominate in the reaction or the products predominate in the reaction. Correct? So the equilibrium constant, it will tell us about the position of the equilibrium. That means what is the relative concentrations of the products as well as the reactants here. The relative concentrations, that means how far the reactants have been converted into the products here. Therefore, the concentration will keep varying. Concentration of the reactants will keep varying here. Okay, that we will be studying in the kinetics here. So, equilibrium constant tells us about the position of the equilibrium. That is it is an expression of the relative concentrations of the starting materials as well and the products at the equilibrium. Once equilibrium is reached, so what is the whether the products predominate in the equilibrium reaction or the reactants predominate in the equilibrium reaction. This is the significance of your equilibrium constant. Now let us see. So we have the numerator and denominator here. Okay, CD numerator and denominator. Okay, if the numerator, the CD, it is higher than AB, what will happen? So CD, that is the concentration of the products, it is more than the product concentration of the reactants, the starting material. That is KEQ, it will be greater than 1 here. Correct? Because CD is higher than AB. The value of CD is more than this thing. That is when K, then equilibrium will, that is one situation here. Okay, this is one position situation, KEQ, it is greater than 1. When CD is more than this thing, that means the reaction favors the formation of the products here. Okay, that is when KEQ is greater than 1, the equilibrium favors, equilibrium favors the products here. That is CD is more compared to AB. The concentration of CD is more. That is the concentration of the products. It is more compared to the concentration of the reactant, starting material. Therefore, the equilibrium or the reaction, the favors the formation of the products here. Therefore, the reaction, the equilibrium lies to the right. We call it equilibrium lies to the right. When KEQ is greater than 1 here. Now, KEQ less than 1. What is the position here? That is less than 1 means CD is less compared to AB here. Okay, the concentration of the products, it will be less than the concentration of the reactant, static material. Therefore, equilibrium favors the formation of the static material. Equilibrium favors the static materials, not the products. Correct? Okay, therefore, the equilibrium reaction will lie to the left side. That is towards the reactant side. Right side is towards the product side. In an equation, if you see, this is the right side here. This is the right side, this is the left side. So the equilibrium, shifts to the, or equilibrium favors this, it lies to the left side means to the side of the reactants. Right side means to the side of the products here. Equilibrium lies to the right means equilibrium favors the formation of the products here. Correct? Okay, equilibrium favors the products here. It will rise to the right side. Now, when KEQ is less than 1, what happens? Equilibrium favors the starting materials here. And it lies to the left side. Now, for a reaction to be useful, what is to be done? Equilibrium must favor products. Correct? That means for a reaction to be useful, the equilibrium should always be greater than, KEQ should be greater than 1. Then only it is of some use to us, because we want the products here. Because there is no point in conducting the reaction without if you don't get the products here. Okay. Therefore, a profitable reaction or an useful reaction, we can say equilibrium must favor the formation of the products here. That is KEQ. It should be greater than 1. Now, again, what determines the equilibrium favor, whether the equilibrium favors the products in a given reaction? Okay. Now, this is only, this is what we want. That is the KEQ should be greater than 1 here. Correct? Now, what determines? Further, let us see. What determines whether equilibrium favors the formation of the products in a reaction? In a given reaction, whether the formation of the products are favored or the formation of the reactants are favored. Now, the position of the equilibrium here, it is determined by the relative energies. Okay, our thermodynamics here. The relative energies. So, the position of the equilibrium, it is determined by the relative energies of what? Energies of the reactants and the relative energies of the products. Okay, that is the position of the equilibrium, that is whether the equilibrium whether the equilibrium favors the formation of the products or whether it favors the formation of the static materials. So that is determined by the relative energies of the static materials as well as the products here. Now, there is a concept called free energy. Free energy, or we can say it is Gibbs free energy, because this is due to Gibbs, a scientist now by name Gibbs here. Okay, free energy or Gibbs free energy. Now let us examine what is the free energy here. This is written by G, that is relative energies we have seen now. Okay, that the position of the equilibrium is determined by the relative energies. We are coming to this concept of the free energy here. Free energy of the reactants and the products here. Okay, now the free energy of a molecule, it is called Gibbs free energy. It is written or represented by G with a superscript like this, or asterisk or whatever it is, and this is the G0 degree, just like degree we write, no, like that we are writing here. Okay, now the change in free energy. Now we are not concerned with the absolute free energy here. The change in free energy, that is delta G again, determined under standard conditions here. Okay, delta G, change in the free energy between the reactants and the products here, that is delta G. It is simple, and this is a symbol being used, delta G here. Okay, it will determine whether the starting material is favored or the products are favored here at equilibrium. So we are concerned, we should know at equilibrium which is being favored, whether the formation of the product is favored or whether the reactance is favored here. Okay, so what determines that? It is the relative energies here. The relative energies of the reactants and relative energies of the products here. That is the free energy. That energy is known as Gibbs free energy or Gibbs energy here, whatever you call it, no? Gibbs free energy. Okay, so it is represented by G. So the the change in free energy, that is delta G, that is between the reactants and the products. That is whether the at equilibrium, whether the products will predominate or whether the reactants will predominate, or whether the products are favored or the reactants are favored. Okay, now delta G, it is the overall energy change. Correct? Delta G, it is the overall energy difference between the reactants and the products. Overall energy difference. Okay. Now, delta G is the overall energy difference between the reactants and the products here. So, this is known as free energy change. Okay. Delta G is the free energy change. So, what is delta G? So, delta G is the free energy change, means that is the energy of the products, G, products, minus G of the reactants. Okay, that is delta G is the G of the products minus G of the reactants here, free energy here. Okay, so this is actually, there is an equation for this one, is minus 2.303 RT, okay, log KEQ. So this is the equation by which we determine the free energy change. Gibbs free energy change minus 2.303 RT. What is T? T is the Kelvin temperature. That is temperature measured in the Kelvin scale, not Celsius. Kelvin temperature. Okay. Now R, it is a gas constant. So again a constant here. Okay. These are all interrelated here. Okay. RT log KEQ. But we are more concerned with the KEQ here. So KEQ, how it is related to the free energy here change. That is the equilibrium constant here. Okay. So we are coming to that point now. So, I will just change the page. So delta G is equal to minus, it is minus actually 2.303 RT log KEQ. Correct? I think we have written this like this only. Minus 2.303 RT log KEQ here. Correct? Now, here R is the gas constant and T is the temperature in the Kelvin scale here. Okay. Now, we can say, now we have to find out what is the relationship between delta G, that is the Gibbs free energy change between the reactants and the products, and the KEQ. What is the relationship? That is what we are going to examine now. KEQ and delta G, how they are interlinked here. Okay, now it is a logarithmic function. Okay, log KEQ minus log KEQ. KEQ depends upon the energy difference here now. Correct? KEQ, that is the equilibrium constant. It depends upon the free energy difference between the reactants and the products here. Now, again, let us assume certain things here. Okay, when KEQ is greater than 1. Greater than 1 means it is a positive number, not negative number. Correct? KEQ is greater than 1. Log KEQ is, how it will be? It will be a positive number. So, KEQ, log KEQ, KEQ is positive. It is greater than 1 means it is a positive number. Correct? So, when KEQ, that is the equilibrium constant, is a positive number, log KEQ, it is a positive number. Simple thing. Okay, therefore, delta G will be negative. Correct? Delta G is minus 2.303 RT log KEQ. Log KEQ, it is a positive number means the entire thing changes into delta G is a negative figure now. Negative number here. KEQ is greater than 1. Log KEQ, it is a positive number. Therefore, delta G is a negative number. Correct? That is, energy is released. Delta G negative means energy released. Okay. Thus, equilibrium, you know that energy released means equilibrium favors the formation of the products here. Okay. That is, energy of the product will be lower here. Why this equilibrium is favoring the formation of the products? Because when energy is released, delta G is negative, that is, energy is released here. Then what happens? The equilibrium favors the products because energy of the products, it will be lower. Energy released means the energy of the product, it will be lower than the energy of the reactants here. Okay. Now, when KEQ is less than 1, let us see. KEQ, equilibrium constant, less than 1 means it's a negative number here. It's a decimal figure. Not negative, it can be a decimal number, not a whole number. Correct? Therefore, when it is less than 1 means log KEQ will be negative. It's a negative number. Correct? KEQ is less than 1. That equilibrium constant, it is less than 1 means log KEQ, it will be a negative number. Therefore, delta G, it will be positive. Because this entire thing is a negative number here. Log KEQ and is a negative means in minus 2.303 is there. Therefore, delta G becomes a positive number here. Correct? When KEQ is less than 1. This is the relationship here. Equilibrium constant and free energy change. Okay. Now, when KEQ is less than 1, the log KEQ, that is equilibrium constant, it is a negative number. Okay. Then the entire delta G, it becomes a positive number. Therefore, energy is absorbed. Positive means energy absorbed. Correct? So, equilibrium favors the formation of the reactants. Correct? When energy is absorbed, that is the reactants formation. It is the energy of the products, it will be higher than the energy of the reactants here. In the earlier case, the energy of the products will be lower than the energy because energy is released. The energy of the product is lower than the energy of the reactants. But here when KEQ, equilibrium constant, is less than 1, delta G becomes positive. Correct. Delta G becomes positive. Therefore, energy is absorbed. Correct. When energy is absorbed, equilibrium favors the formation of the reactants here. The reverse reaction is favored here. Okay. When the energy of the products will become higher than the energy of the reactants here. Okay. This is how we have to relate, the equilibrium constant and the free energy change here. Now, lower energy, it means more stability. You know that. That is, when the molecule or any system it is to be stable enough, the energy should be low. So lower energy means it will be more stable. So equilibrium will favor the products when they are more stable than the static materials there. Okay. Therefore, equilibrium always favors the species which is lower in energy. Correct. That is, lower energy means more stability here. Equilibrium favors the products when the stability is more. That is a lower energy. Correct. Therefore, lower energy means more stability. So equilibrium favors the products when they are more stable. More stable means more stable than the starting materials. Okay, that means of less energy. Correct. The species should be of less energy. Correct. Now let us see. So how will you summarize all these things here? So KEQ less than 1. KEQ is less than 1 means delta G is positive. That is delta, not delta G, it is greater than 0. Correct. This is a simple way we can write here. KEQ, equilibrium constant, is less than 1. Log KEQ is negative. Delta G is positive. Positive means greater than 0. So KEQ less than 1, delta G greater than 0. That is, delta G greater than 0 means more stable reactants here. For example, now the reaction favors the static materials here. Correct. Now, when KEQ it is greater than 1, what happens? Delta G is negative. It is less than 0. One is greater than 0, other one is less than 0. So it becomes a negative now. More stable products will be there here. Correct. KEQ, equilibrium constant, is greater than 1. Delta G less than 0 here. Correct. More stable products, and it will be favoring the formation of the products. Got the point? Equilibrium constant less than 1. The free energy change will be greater than 0. More stable reactants. This is, favoring reactants. Okay. Here it is favoring the products. Okay. Favors the products here. Correct. So this is the basic things here. Okay. Now, briefly, I will tell you what is enthalpy and entropy. There is another concept called entropy, which we will not be dealing too much here in the organic reactions here. So how these things are all interlinked here, I can say. I will not go into mathematical complex derivations and all these kind of things here. Briefly, I will just tell you that is free energy change. This is the free energy change here. Delta G, it is the free energy change. It will depend upon the enthalpy change. This depends upon enthalpy. Free energy change depends upon the enthalpy change, delta H0, and entropy change, delta S0. This is the entropy. Change in entropy. What is entropy? That is the definition given. That is the delta H. It indicates the relative bond strength. Delta H indicates relative bond strength. We have seen that. Relative bond strength. Okay. Now, delta H indicates relative bond strength here. And delta G, we know that free energy change here. Okay, now S, entropy S. What is entropy? Entropy S. Okay, it is a measure of the randomness in a system. Disorder. Randomness or disorder in a system. That is, disorder means the freedom. Correct. The freedom of movement. The more the freedom of movement of the molecules in the system, the more the entropy. That is a simple definition. It is a measure of the randomness or disorder in the system. The more the randomness or the more the disorder, the more the entropy. Correct. That means, the entropy means the more freedom of motion means, or more disorder, it is higher entropy. That is the thing. Randomness or disorder, more disorder. That means, for example, gas molecules. Gas molecules, they are very free to move around here. Therefore, high entropy, we will say, compared to the liquid molecule. And liquid molecules have got a higher entropy compared to the solid molecule. Okay, solid molecules has got very less entropy here because the freedom of movement or the disorder, it is defined in that fashion only. The disorder, the more the entropy. We have to understand in that fashion only. So lower entropy, the solid and liquids have lower entropy compared to the gaseous molecule. Now, a cyclic compound, for example, say we can say cyclic molecules. The movement of the bonds and all restricted bond rotation. Therefore, the entropy rotation, very low entropy there compared to the acyclic molecules here. Acyclic and cyclic. Cyclic entropy is very, very low because very, very restricted bond rotation. The lower energy, entropy. Okay. So these are certain concepts here. Now we will not be dealing too much about entropy. Why, I will tell you. Now entropy change delta S. Here also the delta S, it is a change in the amount of disorder or amount of what you call randomness between the products and the reactants here. Okay, that is delta S positive means the products are more disordered. That is, the randomness is more, the freedom of mobility is more. That is, entropy is very change in entropy. Delta S, is a positive entropy. Change. Delta S positive means the products are more disordered than the reactants. Now delta S negative. Okay, delta S negative means products are less disordered. Okay, or more ordered. Less disordered means more ordered than the reactants here. Okay, now the reactions resulting in, say, in an increase in entropy are always forward. That is a fundamental principle. That is, any reaction, which will favor the an increase in the entropy. Okay, that those reactions are forward. Favored here. Now there is a equation delta G is equal to delta H minus T delta S. So I am just telling you this briefly. That is, this is the energy change, a free energy change here. Okay, that is delta G is the energy change, total energy change, we can say enthalpy change. Delta free energy change. Delta H is the change in the bond energy. Then T is the Kelvin temperature and delta S is the entropy change. Okay, change in entropy. Delta S entropy, change in entropy between the reactants and products. Okay, now total energy change in a reaction, it is due to two factors. Here, as per this thing, change in the bonding energy. This delta H here, it is change in the bond energy. Okay, so delta H here, that is the total energy change in the reaction. It is on account of two factors, we can say here. That is delta G, it is equal to delta H minus T delta S here. The delta H is the change in the bond energy and delta S is change in the disorder, change in the entropy. Okay, therefore, the total energy change in the reaction, that is delta G, it is on account of change in the bond energy, that is delta H, and change in the disorder. Okay, that is change in the bonding energy and change in the disorder. Okay, now the change in the bonding energy, it can be calculated from bond dissociation energy is there. But entropy changes, that is very, very difficult kind of a terminology here. What is meant by this entropy change and all. Okay, so we will not go into that now. So in most of the reactions, let us make an approximation. Let us see here. Delta G, delta H minus T delta S. Okay, delta G is equal to delta H minus T delta S. Okay, so this is the formula we have seen now. So in the most of the reactions, the T delta S, this component here, in this case it is very small compared to the enthalpy term delta H. So compared to this one, this is very small. Therefore we can make an approximation. See, delta G, it is approximately equal to delta H. Okay, and it can be, we can neglect the T delta S can be neglected, because in most of the reactions this is a negligible value, small value compared to the enthalpy change delta H here. Okay, T delta H is a very small one compared to the enthalpy term delta H here. So it can be neglected, correct? Therefore, we will often approximate, we can always, make an approximation here. The overall free energy change of a reaction, it is equivalent to, approximately equal to the overall change in the bonding energy only. So accordingly, we can do one thing. The product is favored in a reaction in which delta H is a negative value. Okay. So that is the bonds in the product are, that the product is favored when delta H will be, okay, delta H is negative. We have seen negative. Delta G we are approximating with the delta H here now. Correct. Therefore, the product is favored in the reaction in which delta H is negative. Now, delta H has got a negative value. That is, the bonds in the product, they are stronger than the bonds in the starting materials, in the reacting materials. The bonds in the product are stronger. Okay, the starting material is favored in which delta H is positive. Correct. These are the final thing which we have to see now. We will ignore this entropy factor here. Okay, now the product is favored here. The formation of the products, it is favored in a reaction in which delta H, it is a negative value. That is, the bonds in the product, they are stronger than the bonds in the reactant static materials. Correct. Now, the static material is favored in which delta H is positive. That is, the bonds in the starting material are stronger compared to the bonds in the product here. Now, two other terms are there here. We have been dealing with endothermic and exothermic reactions here. Now, there is the endergonic. Endergonic reactions. Okay, when delta G is positive, the reaction is named as delta G positive. Then it's known as an endergonic reaction. Okay, then exergonic, just like exothermic, exergonic. When delta G is negative. Okay. Okay. Now we have seen endothermic reaction when delta H is positive, and exothermic reactions when delta H is negative. Correct. Now endergonic reactions, there are two terms, which usually we use this endothermic and exothermic here. Now endergonic and exergonic reactions here. Correct. Now endergonic reaction delta G positive. Okay. Then exergonic reaction delta G negative. Now we have seen endothermic reaction. Endothermic reaction will be delta H positive. Correct. Then exothermic, heat is liberated, released. Reaction delta H will be negative. Okay. So delta G, it is usually approximated here with the delta H. Okay, endergonic reaction delta G positive, exergonic reaction delta G negative, minus. So endothermic reaction delta H is positive, then exothermic reaction delta H is negative here. Now, what we have done, delta G, it is usually approximated, okay, with the delta H. That is the thing which we have written here, delta G, it is usually approximated with delta H. Okay, though, therefore, now endergonic and exergonic and all, we are not using those terminologies now. Okay, now, so I hope you have understood. So in the next class, we will be discussing energy diagrams. The most important aspects here. Energy diagrams we can draw. Reaction and with the energy reaction coordinate. We will be discussing this transition state, and we will be discussing the energy of activation, and we will be plotting the graphs and all, and we will discuss the kinetics aspect of it. So thank you very much for listening.